Hello to everybody. We start our seminar of the Commission The Local Universe. And today, Lorenzo Spina from the Padova Observatory will tell us about planet engulfment events in solar type stars. It is very interesting topic, and it will be good to know what is going in this field. So you are welcome, Lorenzo, to start.
Thank you, Grazina. So this is one of my favorite topics, actually. And as you can guess from the title, today I'm going to talk about what stars eat for dinner. So studying a planet engulfment events in sunlight stars is not only interesting by itself, but as we will see later, it is somehow related to many other intriguing topics, including, for instance, the search of solar systems, analogs of solar systems in the universe. So usually I start with this famous diagram, which describes the demography of exoplanets. And it clearly shows that one of the most interesting discoveries over the history of exoplanet science is that although planetary systems are common in the galaxy, there is a huge diversity among them. And also there is a big difference between the planets in the solar systems and the exoplanetary systems discovered so far. And this diversity is likely the result of severe dynamical processes that have imposed a significant reconfiguration of planetary systems. So it's possible, we think, that in the most dynamical systems, part of the planetary material may have fallen into the hosting stars. And the knowledge of the frequency of these dramatic events in sunlight stars is very important because it will shed light on the possible evolutionary paths of planetary systems and also on the rate of orderly systems similar to our solar system. So that's why it's important to study these dramatic events. And also it's important because in the recent and less recent literature, high-precision spectroscopic studies have unveiled chemical anomalies in stars that have been interpreted as the result or the consequence, if you want, of a planetary engulfment event. Okay, for example, here I'm showing the differential abundances between two components of a binary system as a function of the condensation temperature. So while the two stars look very similar in volatiles, which are the elements that prefer to stay in a gaseous phase, the northern component, this one here, is richer in refractory elements, which are the elements that easily condense in forming rocks like rocky planets and other rocks. So cases like this represent one of the strong points of friction between theory and observations in astrophysics. In fact, stars like these ones that have formed from the same association, they should be chemically identical because they formed from the same cloud at the same time from the same material. So they really should be chemically identical. Instead, we observe anomalies like this. So it's possible, but this is just an hypothesis, that the north component has engulfed a planet which polluted the external convective zone of the star, changing its composition of refractory elements, enhancing its composition of refractory elements. This is just an hypothesis. There is no proof of that. No one has seen this planet falling into the star. Sorry. So there is also an alternative explanation. It's possible that the two stars formed from a cloud that, for any reason that we don't know, was not well mixed. So that the two stars formed with a slightly different composition. So we must resolve this ambiguity because this is not the only case. There are many other binaries with similar anomalies, which may indicate that planet engulfment events are actually quite frequent. So we carried out an experiment that for the first time clearly indicates the nature, the cause of these anomalies, okay? So our experiment is actually very simple, and it is based on two very simple phenomena, which are pollution and dilution. So imagine that you have three sun-like stars with slightly different temperatures. So the colder has a thicker convective envelope, while the hottest has a very thin convective envelope. And now imagine that you throw planets into these stars. So the planetary material will be very well diluted in the thicker convective envelope, and you will not be able to produce any significant change of the stellar composition. However, it will be able to significantly increase the abundance of refractory elements for the hottest star. So therefore, if the anomalies that I showed you before are really due to external pollution of rock material, then the probability of finding anomalous pairs it should be found of the temperature of the stars. So this is the hypothesis that we want to test. And for this test, we used a sample of 107 binary pairs composed by sun-like stars. These pairs are composed by stars that are similar in terms of temperature and gravity, and also they must have an external convective layer. And we divided these stars into classes. 74 chemically homogeneous stars, defined as those whose components have an iron abundance that is similar within 2 times the uncertainty, and 33 chemically anomalous pairs, which are those whose components have different iron abundances. And in this plot, I'm already showing you the results. So this plot shows these 107 pairs as a function of the mean temperatures of their components. And you have already divided the chemically anomalous pairs here in red above, and below the chemically homogeneous pairs. So you can already see by eye that the anomalous pairs are preferentially located on the left side of the diagram. However, we can model that. So we can model the probability of finding anomalous pairs as a function of the temperature. And for this modeling, we have used a sigmoid function that has this, looks like this. And this is the result of our MCMC simulation. So the solid line is the observed average posterior, while the shaded area is the 90% confidence interval of the posterior solutions. And now we can see that given this result, we can see that the probability of finding an anomalous pair among the systems that are composed by hotter stars is higher, and is nearly 50%. So it's quite high, actually. And assuming that the hottest stars change their composition at every single planet engulfment event, and assuming that at least one of the 2 stars of the anomalous pairs has swallowed a planet, we can derive the probability of engulfment events among sun-like stars, which we found is around 0.27, which is quite high. So around 1/3 of stars, of sun-like stars, experience planet engulfment events, according to our observations. And then we also produced a toy model. We produced a mock data set of 500 binary pairs with temperatures within this range, and we randomly polluted the 27% of them with the amount of planetary material that was randomly drawn from a normal distribution. And then we recalculated the probability of finding anomalous pairs, and we found that actually our toy model fits very well with our observation. So basically, our assumption match our observational results. So that's the takeaway from this slide. But can we say something more about the nature of these anomalies? Of course we can. For instance, let's say that we have this system, and this system is anomalous, or in other words, this is the metal-richer star, and this is a metal poorer star. So you can ask to yourself, which is the anomalous star here? Is the metal-rich component that is anomalously richer than it should be? Or is the metal-poor stars which is anomalously poorer of what it should be? So which one of the two is the anomalous? So to answer this question, we compared the iron over carbon abundance ratios of the two stars to the typical values outlined by solar twins. So why iron over carbon ratio? Because this is a proxy of abundance ratios of refractories over volatiles. So if the star has engulfed the planet, it should appear with a higher ratio of refractories over volatiles. So for this comparison, we have taken into account the metallicity and the age of these pairs. So we have compared solar twins of a specific age and metallicity to binary systems of similar age and metallicity, so that we don't compare apples to oranges. So this, if you think that this is the distribution of solar twins as a function of this abundance ratio, so a star that has this value, you can assign it a high percentile rank of iron over carbon, while a star that has this value here would have a low percentile rank. Okay, so we have given a percentile ranks to all the stars in our binary systems, comparing them to the typical distribution of solar twins. And then we have, and this is the result. Okay, let's go to the result. And we can see here the percentile ranks of the metal poor stars and the percentile ranks of the metal rich components of our binary system. And while the metal poor stars more or less have a flat distribution of percentile ranks, here we can see that the metal rich stars preferentially have a high percentile ranks, meaning that the metal rich stars are preferentially located here. So they are anomalous, not only comparing to the other component of the binary system, but they are anomalous comparing to the typical distribution of solar twins, meaning that the metal-rich stars are the anomalous stars. And this is in agreement with this scenario where the metal-rich star is the one that has eaten a planet, okay? So this is another strong indication that these anomalies are actually the smoking guns of planet engulfment events. Okay, and then finally the lithium test. So the lithium is an element that is very strange. It's a peculiar element because it is depleted in stars at different rates depending on the stellar mass. So all stars and all planets are formed with the same reservoir of lithium, but the lithium abundance is decreased in stellar atmosphere as time goes on, simply because lithium is burned into the stellar interior. So for sun-like stars, it's quite easy to say if a star is young or old based on lithium, because young stars have a very deep lithium line like this, while old ones have basically nothing like this. Okay. And here in this plot, for instance, we can see how the abundance of lithium decreases as a function of the age of the stars. So these are solar twins. This is the sun, and we can see that the young solar twins have a very high lithium abundances, and the older solar twins have basically nothing. So of course, imagine that you have an old star which has basically nothing lithium, and this star accretes a planet. So the planet has the origin has a lot of lithium, because a planet does not deplete lithium. So when this happens, the atmosphere of the star get refilled of lithium, and this should appear and this should make the star significantly richer of lithium than what it should be, or than it was before, or than what it should be otherwise. Okay, so this is the hypothesis that we want to test. We want to test this in iron because of planetary engulfment should be rich in lithium as well. Is it true or not? So let's see what data say. Data say that that's true. So we tested this hypothesis on a subsample of our pairs because lithium is depleted at different rates depending on the mass. So we have to choose the binary pairs with stars that are really similar in order we are sure that they must have depleted a very similar amount of lithium. And here we can see, so this diagram here shows the difference in iron as a function of the difference in lithium between the components for each of the binaries. And in blue, again, we have the chemically homogeneous stars, so stars that have a very similar iron abundance, and they also have a very similar lithium abundance with just one exception. While in red, we have the chemically anomalous pairs, so the stars, so the pairs with very different iron abundance, and we can see that these are also the stars that typically also have a very different lithium abundances. Not only that, we also observe that it's always the star that has more iron, the one that also has more lithium. So everything is in agreement with this planetary engulfment scenario. Okay. Okay. So now let's go to the conclusions of this talk. This is a short recap of our main results. So we provided 3 important pieces of evidences indicated that planetary engulfment events can happen in sun-like stars, and we can see that these events can actually change the chemical pattern of a star in a very well-defined way. So iron, also iron over carbon, and also lithium in most of the cases. So we found that planetary engulfment events are quite frequent around stars similar to our sun. That means, so a possible implication is that a non-negligible fraction of suns had very dynamical planetary systems. Okay, instead we are living in a planetary system that seems very ordered and very quiet, almost boring, you know, because all the planets are in very circular orbits. In our solar system also, the rocky planets are in the inner part, the gaseous planets are in the outer part. So there are no evidences of significant dynamical evolution that happened in our solar system. It's possible that at least 1/3 of the stars similar to the sun actually had a very dynamical past, that their system had a very dynamical past. And also we are, so I think that this research is cool. Sorry, it's our research, so it's my research, it's not, but so I think it's important because we are reaching these conclusions not by looking at the planets like most of the other people do, but looking at the stars. And this is not only different, but it's also very important because it will give us complementary information, not completely independent from observations of exoplanets, completely independent from models of evolution of exoplanet, of planetary systems. So we are completely independent, and we can provide information on the same things in a very completely independent. So that's why it's important. So just to conclude, since I've been very quick, I see, just to conclude, I would like to stress what we would like to test in the future. So in the future, we want to test if there is a relation between the chemical composition of stars, of solar twins, and the architecture of planetary systems. For instance, we know that Jupiter in our solar system have played a very important role in setting the architecture of our planetary system. So we would like to see, for instance, if other sun-like stars with Jupiter-like planets, with Jupiter analogs, have a chemical partner that is similar to the one of the sun, or instead is not similar, maybe enriched of refractory elements, which could be the hint of planet engulfment events. And this will be interesting for two main reasons. First, establishing a connection between the chemical composition of stars and the architecture of planetary systems will be very helpful for the future search of Earth-like planets, and also will give us an idea of how rare are planetary systems similar to our own that host life. So in the end, that will be the main question, I think, that we have to address also through our research. Okay, I think I will stop here. Okay, I said these things. So the slide. Okay, and I will take your questions if you have some. Thank you.
Thank you very much, and thank you for raising new ideas for the future research. Now be very quick in working, because other may also do the same. But I think that always there will be not too much information about any question in the universe. So you mentioned that some information of other chemical elements could be useful. So do you plan to investigate the same stars you have for other elements, or new observations you plan to do?
Both. So we need to investigate more in details other elements as well, because we think that one of the signature of chemical engulfment events are these beautiful trends like this. So trends between the differential abundances and the condensation temperature, while we tested only iron and carbon and lithium. So iron is somewhere like here, carbon is here, and lithium is not here in this plot, but it's another, because it's a special element. So, but of course, having more elements would be great. Having more stars would be great. And having more stars with the non-planets will be magnificent. Magnificent will be terrific. So there is a lot to do. The good thing is that with the high-resolution spectrographs like HARPS or Espresso, for instance, you can do both in just one shot. So with I love observing with HARPS. I made a lot of observation with HARPS, and with HARPS you can have the information on the presence or absence of the planet, and also the information on the chemistry. So that's why we need more people that can really exploit the full information locked into this spectra, because most of the people observing with HARPS, they are just observing for planets, but actually you can do a lot with the chemistry as well. So that's really intriguing, and so there is still a lot to do. And but it's important also to focus our research on solar twins, because these are the stars that we can analyze from the chemical point of view with a higher precision, and also we want to know the architecture of the planetary systems around solar twins. So, so in the future we will make new proposals or programs. So we'll try to propose new programs specifically for solar twins, and specifically to tackle these very interesting questions.
Good. This year we published a paper concerning this plot. You have difference of abundances of chemical elements in respect to the condensation temperature, but there were several solar twins, but majority were other stars. And have you noticed we published this year?
Sorry, which data are you talking about?
We investigated dependence on of difference in elements depending on the condensation temperature.
Okay.
So we selected comparison stars from 1,000 of our observations for stars which have exoplanets, and made such comparisons. So maybe you could look what we did and say what else we could do, because we have the telescope with high resolution spectrograph, and we continue those observations.
Yes, definitely. I will look at that paper because it's interesting, and it's one of my main interests. It's very cool topic, I think.
Yes. So please look what we did. And I see the question. Please raise the hand. Please ask Rabchikova.
Cannot hear.
So maybe she will then ask later. So now Vako wishes to...
Okay, thank you very much. Very clear talk. And you mentioned about the possible search for planets for such binary systems. But do you have any example of the binary pair that already planets have been found in your sample?
Yes. So this is an example, and there is a planet around the southern component. There are other, if I'm not wrong, I'm sure that there is a planet around one of these. I think it's around the southern. There are other events. There are other examples. Sorry, 16 Chini and others. But there are few, so there are not many. And so yes, we should continue to observe this, so the presence, to check the presence of planets. And also because, so people, so of course these are binaries, so it's not always trivial to observe planets around binaries, and it's not trivial that these planets can form actually around binaries. So these are wide binaries, so there should be planets, but maybe if I could choose to test, if I could choose a sample to test this eventual correlation between the architecture of planetary system and chemistry, I will not use binaries. Because this binarity could introduce a bias that you don't know. I would use a sample of free stars, of solar twins in the field. And then I would compare them to so their chemical composition to the average composition of solar twins in the solar neighborhood. So that's the way I will proceed. And we had a program that was approved, a large program that was approved years ago. We found some planets. We found some chemical anomalous stars, but we need more observation to increase the baseline. Also because, of course, we cannot find Earth-like planets, but we can find Jupiter planets around these stars, But for Jupiter planets, you need a very long baseline of observations, like more than 10 years maybe, or something like that. So we would like to repeat these observations after that. So now that some years has passed, we would like to repeat these observations in order to check whether or not the chemical anomalous stars are also the one without Jupiter analogs or with Jupiter analogs. So that's the thing that we would like to check.
Okay, thank you very much. And I have one more quick question about the lithium. And you showed the lithium abundance differences for solar twin stars. So are there a subsample of the 107 stars binaries you studied? Yes. Okay, so they have a very similar temperature to the sun, right? No, they have a very similar temperature between themselves. Between themselves. So yes, and also the typical temperatures range from 5,000 to 6,500 Kelvin. So around the solar values, but not exactly the solar value. Okay, but the correlation between age and the lithium abundance is very clear. But I suspect that the lithium abundance is also depends on the mass or temperature of the star. Yes. So yes. So that's why we wanted to let me go there. So do you agree with me that stars that form together, they have the same age? If they have the same mass, they should have the same lithium, regardless their age. So we wanted to test if these stars actually have the same lithium. And we found that it's not always the case for the chemically anomalous pairs. So for instance, if you take this pair here, so the two component is enriched in iron compared to the one component, and also is enriched in lithium compared to the one component. If you take this pair here, it's the opposite. So it's always the star that is richer in iron that is richer in lithium, and not the opposite. With one exception. So this exception here is probably due to the fact that our cuts so sometimes these stars when they go away from the main sequence, they can produce a lot of lithium, okay, in their atmospheres, and that's very sensitive to the mass and all these things. So maybe our cut was not good enough to cut away this one, like, on single exception. But in general, we see that our hypothesis is verified. Okay, and thank you very much. Yeah, I think this is very clear, impressive result. Thank you, thank you. We have another question. No, maybe Grazina? She's freezed, I think. Maybe. Oh, unfortunately. Okay. And let me check some. No. Okay. Okay. I think, yeah, Grazina is coming back. Okay. Hello, Grazina.
Yes. So will we have question from Ryabchuk? probably some internet problems, like in my case.
Yes.
So thank you very much, Lorenzo, and we wish you success, and we will follow your publications. So when you will have new discoveries, please share them with us.
I will.
So,
Thank you very much for this opportunity.
okay.
Bye,
So
bye, bye.
till the